Hi friends, in this video I will explain what is dependency preserving decomposition in database management systems. First let us see what is this dependency preserving decomposition. So whenever you are discussing about the normal forms, if any relation is not in second normal form, so to convert that relation into the second normal form, so we will decompose the relation into smaller relations. Simply here I am dividing this single relation R into two sub relations. So here I am dividing this R into R1 and R2. So this is nothing but the decomposition. Similarly, if I have a relation that is not in third normal form, then also to make this relation into the third normal form, again you have to divide this relation R into sub relations so that it satisfies the properties of third normal form. In all these cases, I am decomposing a relation R into sub relations. So when I am decomposing these relations, so you need to follow mainly two properties. So these two properties are, the first one, dependency preserving decomposition. When I am decomposing a relation, all the dependencies in the relation must be preserved. This is the first property. And the second property is, it must be a lossless decomposition. So whatever the data we have in the relation R, that must be present in the join of these two relations. This is called lossless join dependency. In this video, let us understand what is this dependency preserving decomposition. A dependency preserving decomposition of a relation R is just splitting the relation R1 and R2, R3 and so on Rn. I am splitting this relation R to R1, R2 and so on Rn. When I am splitting this or decomposing this relation R into sub-relations, then this relation R contains some set of functional dependencies. Let us denote it as FD. So FD is the functional dependencies or the set of functional dependencies with respect to the relation R. When I am decomposing into R1, R2 and so on Rn, so each and every relation here R1 can be having the set of functional dependencies, let us take FD1 and this is FD2 and so on FDN. We can derive some set of functional dependencies for each sub relation here. So if you do this, the set of all the functional dependencies of these sub relations can be equivalent to the functional dependencies of the complete relation R. Okay. Here FD1, FD2, FD3 in this equation are the functional dependencies of the sub relations, and the FD1 union, FD2 union and so on FDN plus denotes the closure of union of all sets of these functional dependencies. In simple terms, we can say FD plus is the closure of the functional dependencies with respect to relation R. And when you are doing this decomposition, here I am writing again, there is a relation R, the set of functional dependencies are FD, this is with respect to relation R. Now I am decomposing this relation into R1 and R2. Let us denote here as two sub-relations. We can derive some functional dependencies for R1. Assume this is as F1, and we can also derive some functional dependencies for R2. Now, there may be three possible cases when we can say that dependency is preserved. The union of the functional dependencies FD1 union FD2, if this is equal to this functional dependency, then we can say that decomposition is preserved. If this union of FD1 and FD2 is a subset of this functional dependency, for example, let us say F1 union F2 is only a subset of this functional dependency, then we can say the dependency is not preserved. And another case here, there may be FD1 union FD2, it may be a superset. The functional dependency set FD1 union FD2 may be a superset of this functional dependency with respect to R. But this is not the possible case. So why? Because we are deriving these functional dependencies FD1, FD2 from the functional dependency FD only. So this may not be the case. We will see with an example. Before going to this topic, we have to understand what is trivial functional dependency, non-trivial functional dependency. So what do you mean by this trivial functional dependency? For example, I have a functional dependency in this form: x implies y, x determines y. On the right hand side we have y. So if y is a subset of x, then we can say this functional dependency as trivial functional dependency. Okay, so y is a subset of x. Let us take another equation. If I have a functional dependency A implies B, the right hand side, this is B here, B is a subset of A. Now also we can say this functional dependency as trivial functional dependency. Now we can define what is non-trivial functional dependency. So if I have A implies B, B is not a subset of A. Okay, B is not a subset of A. So if that is a case, we can say this A implies B as a non-trivial functional dependency. Okay, let us take one example for this functional dependency that is trivial. I have an employee ID which can determine employee ID. Okay, so employee ID can determine employee ID. You can observe this. This is a subset of this one. We can say this as trivial functional dependency. For example, I have employee ID and employee name can determine employee ID. If I have functional dependency like this, then also you can see here the right hand side EID. So EID is a subset of EID and name, right? EID is a subset of EID and ename. So this is also a trivial functional dependency. You can take here employee ID can and employee name can determine employee name. So you can see ename is a subset of this X, right? Ename is a subset of this complete part. So it satisfies this. So we can say that this is a trivial functional dependency. For example, I have employee ID implies employee name. So you can see here ename is not a subset of EID. we have only one attribute here, and here we have also one attribute on the right side. So this is ename is not a subset of eid. Okay. For example, if I have eid and ename, okay, can determine e-address. Is this e-address is a subset of eid and name? No. So we can say this as non-trivial functional dependency. Okay. To understand the example of dependency preserving decomposition, so you need to have an idea of what is trivial functional dependency and what is non-trivial functional dependency, so that you will be very clear about the example of this dependency preserving decomposition. Okay. So let us directly start the example. I am taking an example here. So I have a relation R. So this relation is having 4 attributes. Let us denote it as A, B, C, D. There are 4 attributes in the relation R. And this relation is having the functional dependencies FD. Those are AB implies C, C implies D, and D implies A. Here I have the functional dependency FD. This functional dependency FD is for the complete relation R. Fine. Now, this relation R is decomposed into R1 and R2. This relation is decomposed into R1 and R2. So R1 is having the attributes ABC. Okay, R1 is having attributes ABC. R2 is having the attributes C and D. Okay. Now the question is, so whether this decomposition R implies R1 and R2, this decomposition is dependency preserving or not? The question is here, check whether this decomposition dependency preserving or not. Okay, this is the question. Fine. Now, let us take the solution here. We know the relation A, B, C, D are the attributes for R. Okay. And we have the functional dependencies FD here. So you have to find out the functional dependencies FD1. Okay. We have to find out the functional dependencies FD1 and the functional dependencies FD2. How I can get this functional dependency 1 and functional dependency 2? So we can get this functional dependency 1 from relation R1. R1 contains A, B, C, right? From this relation, I can get functional dependency set 1. Assume that as FD1. Then I will get functional dependency set 2 from R2. From R2, I will get functional dependency set 2. Now R2 is having the attributes C and D. C and D. Now if I can get FD1 union FD2 is equal to FD here from this functional dependency, we can say that dependency is preserved. Okay, if I get FD1 union FD2 is equal to functional dependency FD, this is for complete relation. So then we can say dependency is preserved. So if I get FD1 union FD2 is a subset of this functional dependency, then we can say dependency is not preserved. Okay, dependency is not preserved. Now the question is how we can compute this FD1, how we can compute FD2. So simple, this functional dependency set 1 is computed from R1, and we will take these functional dependencies to calculate the functional dependency set 1 and functional dependency set 2. Okay, to find out the functional dependency set FD1, so you have to consider all the combination of this relation R1 with 3 attributes. Take the all possible combinations. Let us take the first one is A, then B, then C, and AB, and BC, and AC, and ABC. Okay, these are the all possible combinations. Fine. Now you have to calculate the closure of these attributes. What is the closure of these attribute? We can denote it as A plus. The closure of this attribute is A plus. If you want to know what is a closure of an attribute, please go and watch my previous video, that is closure of an attribute, and please come back to this video. The closure of this attribute can be denoted as A plus. Okay, so A plus, any attribute can determine, right? The closure of A can be A, and from A can you determine any other attribute? No. And you can observe there is something like A can determine A. A can determine A. So this is like a trivial functional dependency, and the attribute A here is called trivial attribute, right? What do you mean by trivial here? A is a subset of A. So we can say this is a trivial attribute, and this may not be helpful for finding the dependency preserving. Okay, and let us take the attribute B and calculate the closure of this B, and the first attribute we can determine from B is B here. And can we derive any attribute from this? No, right? So we can say B alone is the closure of this attribute. From this, what we can say, B implies B. So this is also trivial functional dependency, right? This is also trivial functional dependency. Now let us calculate the closure of this C, that is C plus. We can denote the closure as C plus plus. And the first attribute we can determine is C. You can observe in this functional dependency, from C we can derive D. So D is one of the attribute in the closure set of C. And here D can determine A. D can determine A here. And any A can determine any other attribute? No. So this is the closure of this one. Now the meaning is, we can say C implies CDA, right? We can determine CDA. But if you observe in this, C is a trivial attribute, so we can ignore this. And D is not the attribute in relation 1. This is a decomposite relation, right? D is not the attribute from R1. R1 is having only A, B, C. So D also can be ignored. Now from this we can say what? C implies A. This is one functional dependency which I got. Okay, I have removed this C in the right side because this is a trivial attribute, right? C is a trivial attribute and D is not present in the R1. So that's why D also I removed. So from this I got a functional dependency C implies A. Fine. Now let us calculate the closure of this AB, that is AB plus. So from this AB we can say A is the first attribute, B is the second attribute. Now A can determine anything here in this? No. B can determine anything in this? No. but AB can determine C, right? So I can say C is one of the attribute, and C again determine D here. D again determines A. So A is already existing in the closure. So ABCD is the closure of AB plus. The meaning of this is what? AB implies ABCD, right? AB implies ABCD. If I write like this, so AB is what? Trivial attributes, right? AB implies AB. So this is something like a trivial attributes. And D is not present in the R1. D is not present in the R1. I am taking FD1. FD1 is calculated from R1. R1 is having only 3 attributes A, B, C. So I am not taking the attribute D here. So the another functional dependency here, what we can say, AB implies C. AB implies C, right? Then I have to calculate the closure of BC plus. B can determine itself, C can determine from this BC, right? Now C can determine D, C can determine D, and D can determine A. Now again I got BC implies BCDA. So what are the trivial attribute here? So BC is like a subset, right? So we can say BC are the trivial attribute, so we can remove this. And D is not part of this R1, so we can remove this. So from this I can say BC can determine A. BC can, here also I am removing BC on the right side because those are the trivial attributes, right? Then I have AC. AC closure is first I am writing A comma C. C can determine what? D here. D can determine A. A is already there. Then B is not there, so AB cannot determine C. So this is the closure. From this, AC implies ACD. So AC are the trivial attributes on the right side. I can remove this. Now I can write what? You can see here D is also not present in this R1. So this also removed. So simply AC implies pi. It is nothing. So there is no such kind of rule. So I can say AC implies pi. That is not at all considered here. And one more, this one. So you can simply ignore this. Why? Because the closure of this ABC is what? ABCD, right? ABCD. So we can say ABC implies ABCD. ABC are the trivial attributes, right? We can remove this ABCD, and D is not belongs to this R1. So we can say ABC implies pi. So this is also not considered. So here I have this functional dependency 1 and 2 and 3. Now similarly I have another relation R2, right? Decomposed relation R2. So what are the attributes in R2? Before, R2 is having C and D. R2 is having C and D. From this I have to calculate FD2. I have to compute FD2. How we can compute FD2? Let us take C, D and CD. All the possible combinations C, D and CD. So you have to calculate the closure of C plus. Okay, C plus. You have to calculate the closure of D plus. You have to calculate the closure of CD plus. If I calculate C closure, then we can say C is the first attribute. C can determine D and D determine A, right? C, D, A. And from this I can say C implies CDA. C is a trivial attribute. A is not part of the relation. So we can say C implies D. C implies D. But here see, D is a part of this R2, right? This is one functional dependency I got. Assume this is as 4. Okay. But you cannot get any other functional dependencies. If required, you can also do the closure of a D and CD closure. So totally I got 4 functional dependencies. Okay. FD1 contains all these three functional dependencies. FD2 contains this functional dependency. Now the thing is, you have to calculate FD1 union FD2. FD1 union FD2. So this FD1 union FD2 contains C implies A, AB implies C, BC implies A, and C implies D. If you observe in this total functional dependency, D implies A, okay? D implies A is not a part of this union set, right? So we can say FD1 union FD2 is a subset of FD. So we can simply say the decomposition is not preserved. Fine. So if I got this FD1 union FD2 is equal to FD, then we can say decomposition, that is dependency preserved. Fine. This is a very simple example. I hope you understood the concept. If you have any queries, please comment in the comment section. Thank you for watching.